The finite volume method in 1 hour or less. The purpose is to give you a very brief introduction to the finite volume method, sufficient so that you can understand most of the parts in the commercial software that we will be using in this course. Let's begin by the conservation equations. The finite volume methods use the integral form of the conservation equations. So here you can see a generic transport equation in which we have on the left hand side we have a transient term, then we have a convective term, and the first term on the right hand side is a diffusive term, and then we have some sort of source term. So here is the main difference, I would say, between the finite element method and the finite difference method, that more or less work on the differential generic transport equation rather than the integral form of the transport equation. So the first step that you need to take is to identify the system, and I strongly recommend that you keep it short and simple. First of all, is it possible to find any analytical solution to this problem? If you have it, then there's no need to set up a complex computer model. Then you have to think about the physics. Do we have incompressible flow? Is it isothermal? Do we have perhaps reactions? How about turbulence? Yeah, and then you have to apply the correct boundaries, and if you don't have the correct boundaries, you can never expect to have a reasonable solution. And finally, also think about what results you're expecting. Okay, let's take an example. Find the pressure drop between the points A and B. Here A represents the inlet and B represents the outlet. Well, in this case, perhaps we could use Bernoulli's equation and the continuity equation. So then we have some assumption of incompressible flow, and we assume further that it's steady state as well. You see the Bernoulli equation and you see the continuity equation. So if the purpose is to find the pressure drop between the inlet and outlet, then we need the friction factor in the Bernoulli equation. So let's look at that. We have all these terms are of course divided by the mass flow of the system, but anyhow they sort of represents the kinetic energy. This is the potential energy, this is the pressure energy term, and this is the energy losses due to friction and energy due to work done by the system. So this frictional losses, to estimate those we need the friction factor, and that can be very difficult to estimate. In some cases we have it from several experiments, but in complex systems we most likely do not have it. And if we cannot estimate the friction factor, then what? Well, in that case, let's use the finite volume method. So you can imagine that in this backward facing step example, we will have not just smooth straight streamlines, but you can see just behind the step we have the likelihood of a recirculating region where the fluid flow is not going in a straight manner, but it's circulating. This is of course part of a friction factor if we would use it in the Bernoulli equation. But with the finite volume method we can resolve this system in such a manner that we could actually see how this interacts with the pressure loss. So okay, before starting with the finite volume method, ask yourself a question. What should you ask yourself before trying to solve a fluid flow problem? So Computational Fluid Dynamics, or CFD, begins by creating the domain, and then we discretize the domain. So we generate a grid or mesh. We divide it into smaller parts over which we solve the fluid flow equations. And then we also need to discretize the equations. We need to express them in a numerical manner. And then we solve the equations, and finally we analyze the results. That's commonly known as post-processing. So the finite difference method, finite volume method, and finite element method all use these particular steps. And if we look at it, the main difference when we compare the finite difference and finite element methods with the finite volume method comes in the discretization part of the domain and the equations. Otherwise, it has many similarities. The discretization of the domain, instead of making a flux balance between the inlet and outlet, we can divide this system into several smaller parts. For instance, like this. Let's just divide it into several quadrilaterals in 2D. In fact, usually in many finite volume codes, we never solve it in 2 dimensions or in 1 dimension, because we assume that we have unit length in the other direction. So here, if we would solve this in the XY plane, the C direction would be of unit length. So we have a real volume over which we solve the equation. And it becomes easier because density will remain to have units of mass per unit volume instead of mass per unit area, or mass per unit length if we have in 1 dimension. So we keep the units that we are familiar with by using this approach. Anyhow, this is a structured mesh, and what that means is that, okay, we can perhaps draw some further. If we imagine that this mesh continues here, we're not solving in these cells that lie outside of the domain, but they are there. In this case, we can go into one of the cells, and this cell is connected to 4 neighbors, and just by the structure of the mesh we know what neighbors these are. We don't need any further information. We know that if we have a certain number in the horizontal direction, we can just add that number to get the cell number above, or we can subtract that number to get the cell number below. We can add 1 or subtract 1 to get the side cell numbers. So this is a structured mesh. We could also create a mesh that is curvilinear, so it curves around the shape of some wall, for instance. But this can also be structured. So as you see, if we take this cell, for instance, we can use the same principle as in the previous example. We can add the number of, well, let's say horizontal cells here to get this cell number, and subtract it to get this cell number. Subtract 1 to get this cell, and add 1 to get this cell. So still, this is a structured mesh. Then we can also use a completely unstructured mesh. And I've chosen triangles here because they are most commonly associated with unstructured meshing. But the purpose with an unstructured mesh is to easily conform to very complex geometries. The difficulty in this case is that there is no logical structure to what cell numbers are connected to this cell. Okay, we can see that it's these 3 cells, but we don't easily know what numbers they have. So we need some form of list in our computer program to determine what cells are connected to what cells. And just a small note here, that a solver that can handle both structured and unstructured meshes will interpret all meshes as unstructured. So this normally increases solution time and computer memory requirements. But anyhow, it's just the cost of being general. There are many benefits to having a structured mesh anyhow when solving the equations. If it's possible, then structured meshes should always be used. So let's discretize the equations. Let's say that we wish to solve some diffusion equation. Here we have the heat equation with the source term in a steady state. Then the finite volume method begins by putting this in the integral form, as you can see. So we simply integrate the expression over the entire control volume. And here the divergence theorem can be used, which states that the volume integral over the divergence of some variable phi here equals the surface integral times the surface normal times this variable phi. So if we can determine the surface normals and the surface areas, we can approximate the fluxes over the entire surfaces. So basically this means that we can rewrite this volume integral expression to a surface integral expression and calculate the fluxes over the surfaces. So in one dimension this can be done in the following manner. We have a one-dimensional domain, and normally we call the central nodal point P, and around that point we create a control volume. And the west surface is denoted by small w, and the east surface is denoted by small e. And the length of the control volume is delta x here. So this means that we can write the integral, the surface integral, as the west side plus the east side plus the mean source term over the control volume. Here you can see that the surface normal is defined as pointing out from, here you can see, out from the control volume. And this is the normal definition. So if we go back and look at the transport phenomena when we derive the equations of change, this seems quite similar, right? So instead of starting with the integral expression and reaching the differential expression at the end, we start with the differential expression and go back to the integral flux expression. So how do we evaluate these values at the east and the west surfaces? We can extend this one-dimensional domain a bit to have a look at what neighbors we do have. Normally we name the neighbors or the nodes with the capital letters, minor letters for the surfaces of the control volumes. And remember now that data is stored at the nodes, so we have no data storage at the west and the east surfaces. So we need to evaluate them by some interpolation. So for instance, the conductivity, if we wish to evaluate that at the west control surface, then we can use some linear interpolation. And this works well if the grid is uniform. Similarly for the east surface. The diffusive flux can be evaluated in the following manner. We have the derivative of temperature, and if we use a central difference of that derivative, then the numerical representation is the following. And we can use a central difference for the gradient at the east control volume surface as well. Finally, we arrive at the discretized equation for the node P, and this will create a very large system of equations that we need to solve in some manner in order to get the results. But before we can solve it, we need reasonable boundary conditions. And in essence, there are two different boundary conditions that we can apply. We either have a Dirichlet boundary condition or a von Neumann boundary condition. If I give you some examples for the heat equation, look at the control volume close to a wall. The wall surface is named A in this case, and the value of the variable is known at the boundary if we have a Dirichlet boundary condition. So for instance, if it's temperature, we could say that the temperature is 500 kelvins at the wall. And one interesting thing here is that for our interpolations, you can imagine that we have an imaginary control volume here on the outside of the wall. It doesn't exist because we're only solving for the interior cells, right? So this does not exist, but it would be named capital W. But it does not exist. Instead, we use interpolation like this to find the value of T capital W. So this is the interpolation. So with the Neumann boundary condition, we know the gradient of the variable at the boundary. So then we can state that the west side gradient here is known. And we can input it directly into the flux expression for this control volume. So some important boundary conditions that are based on these is the velocity inlet, where we have a fixed velocity given at the inlet. We have the pressure outlet, where we have a pressure given. We have walls, where we have a combination of Dirichlet and von Neumann boundary conditions for velocity and pressure. We also have symmetry or axis symmetry conditions that are zero flux, von Neumann boundary conditions as well. Okay, going on to slightly more complex equation. If we have convection combined with diffusion, then our equation contains this part as well, where we have a velocity that's convecting this energy. To solve this with the finite volume method, we do it in the same manner as before. We start by integrating over the control volume, and we apply the divergence theorem. And now we have not only the diffusive terms in our numerical representation of this control volume flux, we also have some convective terms. And it's quite common to lump some of these terms into the letter F here for flux. So how do we actually approximate the convective terms at the control volume surfaces? Well, we can use a central difference as before. So this is similar to the treatment that we used for the diffusive terms previously. We can also use upwinding, and in upwinding we assume that there is a bias towards the upwind side of the flow. So whatever variable we have on the upwind side will prevail at the control volume surface. So if the flow is going from west to east, then we would use the temperature at the west node here for this control volume surface on the west side of this node P. And similarly, if the flow is going from east to west, we would use the temperature at the east node for the control volume surface. Central difference is more accurate, but it can lead to unbounded results, and is generally not incorporated into commercial software. First order upwind causes a lot of numerical diffusion, but it is much more stable, and most commercial software has it as an option to use. In Fluent we have a second order upwind as the default scheme, and it is robust and accurate, so generally it is a good choice. Okay, so this will conclude this very brief primer to the topic.